Well, here we are at Chem Advantage and WebAssign. This, the assignment, one of the most challenging of the year, involves buffers and titrations. That strikes fear into the heart of AP students. I hope you've already gone to the AP Classroom site where you can find an outline that explains buffers and titration curves and have some videos that explain everything that's going on. But let's get back to the problem set. And also, don't forget that you've got a discussion board that you can use to ask questions. So, this is the assignment, and we've got a whole host of questions in it. Let's go to the toughest one right now. Let's take this and see if we can figure out how to solve this question. Here we are, question number 15. It's a beauty. It involves so much of acids and bases that if you can handle this, you can feel confident on the AP section that covers acids and bases. I'm going to break this down into each part of the question. Here you can see the entire thing. We've got a titration curve. We've got pHs. We've got a partial titration and asking about pHs and all the rest. Well, let's read the problem. We're going to start with hypochlorous acid, a mouthful, HOCl, a weak acid. Let me take a little diversion here to naming acids. With acids, we start off with the polyatomic ion that is the anion that makes up the acid. Here, in this case, we've got the common one everybody should memorize, which is chlorate with a charge of -1. And you can give it an extra oxygen. So to indicate that, you'd call it perchlorate. And then chlorite has one less oxygen, and then hypo, which means under, has even one less than that, and that's where we get this ion that we'll be dealing with. And ultimately, you can have just the chloride ion that has that -1. These all have got a -1 charge. The -1 ends up being a result of how the oxygen and the chlorine control things. Oxygen has an oxidation number of -2. 4 of those oxygens will give you a -8. So the chlorine has an oxidation number of +7 to counteract that -8 and still have a -1 charge. Then we have a +5 oxidation number for chlorine, then for chlorine and chlorate, and then in chlorite it has a +3, and down to hypochlorite it has just a +1, and with the one oxygen it gives you a -1. And then finally you've got chloride where it's got this negative charge. All these chlorates are pretty reactive, all the way up to the chloride, because they change their oxidation number to try and get down to this chloride -1. When you make the acid, you sort of take your original arrangement, and a 8 becomes a chloric. So basically you start with the 8, and that becomes the ic acid. And then, of course, that makes perchloric acid. The ites become an OUS acid, and then we have hypochlorous acid, and then we've got our solution of HCl, which is called hydrochloric acid. The naming isn't officially in the AP system. Most colleges would expect that you'd understand the naming of oxo acids, so that's why I put this little review in. But on to our problem. We've got our hypochlorous acid, and we have a Ka expression, which tells us about how strong or weak the acid is, because HOCl is in our list of strong acids. We know it would be a weak one, and they give us a pretty low Ka. This is 10 to the -8. That's a pretty low value. Now, when you're doing these problems, I always advise, if you get the Ka, to figure out the pKa, the p value of it, because it'll come in handy. So let me put my calculator up, and I'm going to take the negative log of Ka value, our 3.2, and of course raise it to that -8 value. That'll give us the pKa, about 7.49. That sort of makes sense. With a 10 to the -8, you'd expect a p-value in the area of a little bit more than 7, and that's what we've got. So I'd write that down, because as I say, it's going to come in handy later on whenever you have a tough or long problem involving a weak acid. pKa 7.49. When you have an equal mixture of this acid as conjugate base, you'll have this pH, 7.49. But let's go on to the problem here. Write a chemical equation showing how hypochlorous acid behaves as an acid in water. Okay, chemical equation showing how the acid reacts. Naturally, we'll start with our acid, hypochlorous acid. Behaves in water, we add it to water. There's our H2O. And then this is a weak acid, so it behooves you to put in our little equilibrium sign because we run into an equilibrium. If you just use an arrow, it wouldn't be marked wrong on an FRQ, but this is a good reminder of how to treat this, that you'll have to deal with equilibrium. And it's an acid. We want to see how it behaves as an acid, so we would know it's going to produce H3O plus. This proton would be donated to the H2O to give it H3 with a plus charge. That is the action of an acid. This is the weak acid, so it only happens partially. It's not much of it is going to be making H3O plus. And of course, we have left over OCl, which has lost that proton and becomes our conjugate base. Now, in weak acid-base reaction, the original acid and the conjugate are pretty important because they battle one another to determine how much of this H3O plus we get. So we've gotten this. If this was an FRQ, which this question is based on, you have yourself 1 point that gets you started. Well, we've got 1 point. Let's go to the next. B, calculate the pH of a 0.5 molar solution of HOCl. Well, when you're doing this at WebAssign, you're going to have a different value than I have because I put a random number generator in here. So when you do this problem, your numbers can be different, but we'll follow the same procedure. So let me get back to my example where I'm solving this. We have a 0.25 molar solution of HOCl. Well, we've got an equilibrium situation. This is the long way of doing things, where we presume that we have 1 liter and we've got our original equation. Now, I didn't use this version of the equation because that's a bit too complicated. You can always simplify it to this version. And that also helps you because this Ka that's given on the AP equation sheet is one that follows the simplified version where we get rid of the H2O. This H2O is gone and the H2O of the H3O plus is gone. So we have just this part. And we're starting off. This is our ice chart, our initial amount. This is a mole in a liter. And we have 0.25 molar solution. So that's what we start with. This is just dumping it in water. We're not doing anything else. So we don't have to worry about the H plus concentration. There's a little bit in there, 10 to the negative 7 initially when it's neutral, but we're not going to worry about that. This doesn't have any OCl. This just makes this a simple weak acid problem because we're having a solution with nothing else but HOCl in it. But that's not going to last for long because some of that acid is going to react with the water to make H plus and our conjugate base. So we're going to lose some of this, gain this, but this is a weak acid. Look, 3 times 10 to the negative 8, that's not going to be much at all. So at equilibrium, when this equation is valid, we would have 0.25 minus the amount that ionized. So we have this original acid we dumped in, 0.25 moles in a liter of water, reduced a little bit. And some of that little bit will become the acid. That's going to determine our pH. We're going to have a little bit of our conjugate base in there. And that conjugate base, of course, is what reacts with H plus to make our OCl back again. If we're going to plug this equilibrium situation into our Ka equation, and let's put those numbers in, or those values at equilibrium, we have our 3.2 times 10 to the negative 8. I didn't put the extra decimal point in there, but here we are. So let's see if we can calculate this, and I'll pull up my calculator. This is a quadratic, so I'm going to go to my math and go to the numeric solver, and I've already put in the 3.2 times 10 to the negative 8. I wanted to show you how you put the rest of the equation in if you wanted to solve this using the quadratic, which is really not the way to go. Now, I'm going to use x. Now, you could use an alpha and then find x here somewhere. There it is. But it's much easier just to use this one key. You want to keep things simple. Squared divided by parentheses. And I've got my 0.25 minus, and again, easy to use x. Close my parentheses. Double check my equation. X squared, 0.25. I put all this in. I've got the right values. Time to enter. I'll set my x at 0. This is a quadratic, so you'll have 2 solutions. So I'm going to start at 0. I don't want to have the negative value. That you can get for this. And then I'm going to use graph here that indicates the solve, or I could use the second function, I should say alpha function, solve, to do the solution, but this is a little bit easier. Save a keystroke, and there I get a value. Notice it carries it out to a ridiculous number of significant digits. Nobody's ever measured a hydrogen ion concentration at that level. If you put this number down in your answer, the poor grader will say, oh, what's wrong with this? Why'd they waste all that pen? Because that's impossible. And they won't think well of you, really. Times 10 to the negative 5. So we could enter that to 3 significant digits, 8.94 times 10 to the negative 5. So that's a small amount. That's what we'd expect. Now, that, of course, is the long way. And this is sort of the ideal solution, but you really shouldn't follow that method if you're doing an FRQ. FRQs are long, and you don't want to not be able to answer the last question on this because you ran out of time. There's a much faster method that's accepted for FRQs to come up with a simple situation where you have a weak acid and they give you its Ka and they want you to find out the hydrogen ion concentration. Let me pull up my outline. This is the original method of solution. And notice that in this original long method of my outline, it says the x will always be small, so you don't have to worry about this minus x. We could have used just 0.25 in our answer, and then we wouldn't have to use a quadratic. We could use simple math, where you just have 0.25 times Ka, then take a square root. But really what you should do is remember this simple method for weak acids, that the concentration of the acid is going to be approximately equal to the original concentration of the acid times the Ka square rooted. Much faster. If you put that down, showing your work, you're set. The reason I go through all of this is because this explains what happens. It's the ideal arrangement. But you need to save some time. Just follow that. Concentration of the acid times the Ka. And I'll put my calculator up. And this is an approximation. Here's my original calculation. There you can see I got the pKa. And now I'm going to take second function square root, take the 0.25 times my 3.2, second function e, negative 8, and there's my answer. In fact, let's go back to our math mode, look at our numeric solver, where we solved. We got 8.9426 and 8.944. Very, very close to 3 significant digits. You're set. That really is going to give us our answer. So we can say our hydrogen ion concentration is going to be that value. If you have an FRQ, you should make things pretty obvious. I would circle this and say this is the hydrogen ion concentration, and using this method is going to save you a couple of minutes. We're set with that part of the problem. This is probably going to be worth 2 points. If you show your calculation using your original concentration times this, if you showed this, that's fine too. Now, let's go to the last part of the problem where they ask for the pH. By now, you shouldn't have to look up the equation sheet to find out how to get a pH, which is the negative log of the acid concentration. But let's go back to our calculator. Since I've already solved for x, I can just say negative log, the value I got for the solver, or I could have put in the second function answer and gotten that too. And there we go. Now I'm going to look at this. I'm going to say 4, that's good. This is a weak acid. This is a pH that indicates that we have a slightly acidic solution, one that you can wash your hands in. This is not nearly dangerous in terms of acidity. Probably should have shown that calculation here somewhere where I would have negative equals negative log, because you have to show a little bit of work so they know that you're not cheating. Here we've got probably now 3 points out of a typical FRQ that would be worth 10 points. Now, before I go on to the next part of this problem, I want to look things over again. Here at equilibrium now, we have a 0.25 molar, roughly, HOCl. We have a hydrogen ion concentration of a decimal point, 1, 2, 3, 4, 9 value of hydrogen ions, and the same for the OCl. Now, I've got a diagram here I wanted to sort of represent so you've got an idea of what's happening. Here we have just this flask. All we've done is add a bunch of HOCl, our weak acid. A few of these molecules have broken up to make H plus and OCl. They're sort of mixing it up. Some of the H plus and OCl is turning back into HOCl, and some of the HOCl is turning into H plus and OCl. And we've got that equilibrium established where we have the concentration that we've figured out in our problem. So we've got mostly HOCl with a little bit of H plus and OCl minus in our flask. So here's the solution to our problem. We've written the chemical equation for hypochlorous acid reacting with water, and we've calculated the pH of the HOCl, first by finding the hydrogen ion concentration using some simple equations. And then using that hydrogen ion concentration, we were able to easily show and figure out what the pH is. In doing an FRQ, this really is all you'd have to write out because you've shown your work, you've checked things out to make sure everything is right, and we've got the solutions, pH and the chemical equation. So you can now go to the next video where we'll keep on working on this FRQ.